Hello everyone, I'm Lou Del Monte and welcome to Del Monte on Science. This is part 2 and we're discussing dark matter and the mysteries associated with dark matter. And in the first video we discussed how the discoveries that led to the discovery of dark matter. Now we're going to look into the science of it. Today, there's a school of thought that says dark matter is a particle, and they call it the WIMP particle. Okay, this is what the school of thought that says that dark matter is a particle. And what does WIMP mean? It means weakly interactive massive particle. So it's not interacting with anything. It has a lot of mass because it bends light. We notice it bends light. And it's accounting for, and I'll give you the numbers, but it's accounting for a significant portion of the mass of the universe, over 90% of it. And that it's a weakly interactive massive particle. All right, so the Department of Energy, Fermilab, okay, so now we're talking about the Department of Energy, and specifically we're talking about Fermilab, begins to look for the WIMP particle. And so one of the laboratories is in an abandoned iron mine in Soudan, Minnesota, which is roughly about 100 or so miles from my house. And they're searching, they're a half mile deep into the earth. And the idea is that the earth is filtering out a lot of the other particles that they would have to contend with, and that they're looking for this weakly interactive massive particle which would go through that half mile of earth, and they've got a cryogenic detector and they're trying to detect it. Okay, this has been going on well, for quite some time actually. We're probably looking at a number of years, but in 2009 they detect two events that are consistent with dark matter, okay? And they make a statement about it, and they put cautions around it and what have you. But they have a criteria that there has to be one, that for this to be a valid result, there has to be one part in 1,000 chance that they're wrong. And it doesn't pass that test. So they're not ready to come out and say, we've discovered the dark matter particle. But they begin upgrading in 2010. Now 2010, they start upgrading the detector, and the idea is that they continue to look for it. Now, a number of other agencies, including the University of Minnesota, have all been looking for and working with, in some cases, Fermilab. No one has definitively found this quote particle. Now, to make matters just a little bit worse, as if they could get any worse at this point, the standard model of particle physics, okay, so standard model of particle physics, which is considered one of the great theories and of modern science, that it predicted the tau neutrino before we found it and things like that. It's an excellent model of particle physics. In its form, it was actually brought to a a very sophisticated form in approximately the 1970s. In that form, in that sophisticated form, it did not predict that we would find a dark matter particle. And that's a big whoops. If the standard model of particle physics says you're not finding we don't predict the dark matter particle, then we got a problem. However, what they've done is they made modifications to the standard model, okay? And the modifications had to do with what they call supersymmetry theory. And it's an extension to the standard model. And what they're doing, if you look at particle physics, in a quantum mechanical sense, there is a property called spin related to particles, and they look at how spin is conserved, and they look at supersymmetry as a conservation of spin. And basically what happens is, if you modify the standard model with this, you can get it to predict some other particles. And one of the particles is the WIMP. Okay? Now you would say, that's great. We finally got something that's predicting it. The supersymmetry aspects, this modification, and all the particles that it predicted have never been found. To make matters worse, the scientists at CERN, where the CERN is where the Large Hadron Collider is. Okay, that's the biggest collider in the world. They've been looking for dark matter and trying to create it in the laboratory. And they have said that they don't see supersymmetry. They can't confirm that that's real. And as a point of fact, they actually say that the theory should be abandoned. So they're saying this is wrong based on experimental results. So where are we left? We're left with the fact that the best models of accepted physics don't predict a WIMP particle. Now, you know, being a scientist, myself, you have to go with the data. Okay, it's fine to have imagination, you need imagination, fine to have theories, but they have to be testable and you have to go with the data. And the data says that we haven't found it after 10 years of looking, we haven't found it, and that there's a good chance the best theories we have in science don't predict it. There's a good chance that it doesn't exist. What does exist? What do we really know? You know, we know three things. We know that dark matter is not in the visible spectrum because we don't see it. We know that it doesn't strongly interact with other forms of energy or matter. Okay, we know that. And we know that it exhibits a gravitational pull on light. And lastly, we know that it is mainly concentrated, primarily concentrated, in and around galaxies, and that we don't find any evidence of dark matter between galaxies. All right, so where do we go from here? Well, if it's not a particle, if this is the case, if it's not this, draw the not sign here, if it's not that, then maybe we should start looking at it as energy. You know, because, and you might say, well, then how does energy exhibit a gravitational attraction? Well, you have E equals mc squared, and that's Einstein's famous mass-energy equivalent. Anytime I have energy, I have implied mass. So if I have energy, in effect, I have mass. Now, where is the energy? Okay, so I've got this energy, where is it? Well, you know, basically, and this is speculative, but I think that M-theory gives us a clue. M-theory says that there's 11 dimensions. There's 11, not just the 4 that we normally experience, X, Y, and Z in time, but 11 dimensions. And it's entirely possible. M-theory itself is not proven, all right? But it is a theory of science. It's entirely possible that there are other dimensions that this energy could be in, and that it's a relatively small amount of energy, and that we don't detect it per se. Very similar to the way we don't detect virtual particles. All right, so what do I suggest? I suggest that we do missing mass experiments in the colliders, especially the Large Hadron Collider. Because if you can do a missing mass experiment, and that is that you have particles collide, you have 2 particles collide at very high energies, and when they collide, you account for all the mass and energy that exists after the collision. If anything is missing, you could make a case that the missing energy is in one of the hidden dimensions of M-theory. Okay, and so that would be a path to begin to investigate, are we really dealing with an energy and not a particle per se? So with that, I'll leave you with that as food for thought. I appreciate you joining me for this session of dark matter. It is a mystery. It continues to be a mystery. I've come to the personal belief that we're really not dealing with a particle, that we're dealing with energy. Thank you very much.